Hi everyone, in the chapter 10, we are going to cover solid liquids and their intermolecular forces. Okay, so the overview for this chapter is going to include the first lecture, which is intermolecular forces, and then I'm going to go over property of liquids and also phase transition, and then we are going to finish up with the phase diagram. And here is the overview and the learning outcome for this chapter 10. Okay, let's start with 10.1, which is the intermolecular forces. Okay, so when I refer to intermolecular forces, it's going to refer to the force between molecule. If you have two molecules, it's between that, it's not within. Okay, so this is between the two molecules. So these intermolecular forces, or IMF, is going to responsible for the behavior of liquid and solid, that's which we are going to cover for this chapter chapter 10. Okay, so I have an activity for you before you actually start watching the rest of the video. Is I would like you to pause the video and start read chapter 10.1, and after you finish reading, then I would like you to fill out what you understand from reading with this exercise number 1. Okay, so again, pause the video now and then read the chapter 10.1 OER textbook, and then fill out this exercise 1, and then resume the video again when you are ready. Now let's check your work together. Okay, so in this exercise number one, we are going to take a look at the relationship between kinetics energy, intermolecular forces, and state of matter. Okay, so if you're looking at which state that has the lowest kinetics energy, the answer for that would be solid, right? Because solid stay close together, they are going to have the least motion, right? So they are going to have only vibration. That's all it can do. And because they are tight packed together, therefore solid would have the strongest intermolecular forces, right? Because they tie together, they are going to what do you call it, interact with each other the most, right? If you are compared that with gas would disperse throughout a container, therefore it's going to not interact with each other much at all, which is going to fall into the kinetic molecular theory that we learned in chapter 9, right? So that's gas molecule do not interact. So therefore, in this case, gas would have a lot of degree of freedom, right, to move. Therefore, it's going to have the highest kinetics energy. Okay. So let's take a look at exercise 1, number 2. Okay, so this one, we are going to take a look at the state change, right? So we can see that many gases can be liquefied by compression, right, at low temperature. So at low temperature, gases can change state, right, from gas to liquid. Okay, the increased pressure bring the molecules of a gas closer together. Okay, so as as the pressure increase, molecule get closer together, such that the attraction between the molecules become stronger, right? So now because they are get closer, so they are going to be able to interact with each other stronger, right, relative to their kinetics energy. Consequently, the molecules change their state from gas to liquid. Okay, so this is how we are going to move or transition from gas to liquid and solid state now, right? So in chapter 9, right, we are looking at gas, right? So we're looking at how gas can expand to fill its container, highly compressible. The reason why it's highly compressible is because what we just talked about here, right? So because at low temperature, you can compress it, right, with high pressure as well to bring all those molecules to get closer together so that you increase the IMF and you decrease kinetics energy. So consequently, it's changed from gas to liquid. In chapter 9, we focus our attention to only gas, right? So we looking at the kinetic molecular theory, right, that gas do not interact at all, right? So according to what we see, the reason for that is because it have a very high kinetics energy. One, it have all the degree of freedom, right? It doesn't have any interaction at all, right? So therefore, in this case, we can assume that there should be no force that hold them together. So that means we can assume, so according to the ideal gas behavior, we assume that all the gas molecule will not interact with each other, right? So in this chapter 10, we are going to actually focus our attention on only solid and liquid. Okay, so these two states are going to be more dense, like a denser state. Okay, so which means these two are going to pretty much have the IMF or intermolecular forces appear within them. Okay, so because it's required those two forces to hold them close together to have them in a dense state. Okay, So pretty much the IMF and also kinetics energy, these two are going to control state of matter, as I mentioned earlier. Okay. So let's take a look at this. Okay, so more graphical representation right here is that if you have gas, right, you can compress it by increasing the pressure, right, or reduce temperature. So in this case, as you decrease the pressure, gas molecules get closer together, so they have more chance to interact. So therefore, it's going to change state to liquid, right? So, but if you compare this with liquid, right, liquid molecules closely packed already, so they are not easily compressible. Okay, so if we're looking at how the change between state happen, and we tie that back into temperature and kinetics energy and also IMF, we can see this, right? So as you increase temperature, you are increasing kinetics energy. So therefore, in this case, molecule has going to be able to move more, right? Because as the temperature increase, kinetics energy increase, the motions will also increase as well. So in this case, as you increase further, right, you are going to eventually reduce the intermolecular forces, and that is going to cause the state of matter to change form, right? So from, for example, solid to liquid and to gas. Vice versa, if you cool it down or you decrease the temperature, you are also decreasing kinetic energy as well. So in this case, molecule gonna stay closer together, so the IMF would increase, right? So that's how you change from gas to liquid and to solid. Next, before we get into more detail of intermolecular forces, we need to actually define first what it is exactly, right? So intermolecular forces would be the force between molecules. Okay, so for example, if you have molecule of HCl, right? This is molecule the first one, right? And then this is HClB, right? So the second molecule, the force between these two, this is what we refer as intermolecular forces, is between, right? Inter is between. So this is between the two molecules. Okay, so this is between. In Chem 121, however, we learn the force within the molecule. Okay, so this is referred as intra. Okay, so this is within. Okay, so this force right here is what we refer as covalent bond. If you have the two non-metal combined, right? So this is what we cover in Chem 121. Okay, so when you have two non-metal, right, to form bonds, so that is going to refer as covalent bonds. Okay, so I'm not going to talk much about intramolecular forces because we already learned about covalent bond in Chem 121. You will learn about how to draw the structure. You learn how to name molecular compound. Also, you also learn about the formation of covalent bond as well, right? So all of this, we already covered that in Chem 121. But in Chem 122, we are going to focus our attention for the force between the molecule instead. Okay, so that's what we're going to take a look at. Okay, so there are different type of IMFs all together, of different type or combined together, we call it as van der Waals forces. Okay, so van der Waals forces is referred as like everything within umbrella of like IMFs. Okay, so why is this important? Okay, so we're gonna take a look at next. Okay, so the strength of the IMF is actually determine the state of matter. So what I would like you to look at is these three picture right here. So these are chlorine, bromine, iodide, okay, molecules. Okay, so these are the compound that is going to be part of the element in group 7A. Okay, so on the periodic table, these are in group 7A. So they are on the same group. They should, so they behave this like their property should be similar, right? So in terms of reactivity. However, in this case, the state of matter, they have different state of matter. So why is that, right? So how come that chlorine is gas? If you're looking at bromine, it's liquid, and if you're looking at iodine, right, it's solid. So why is that, right? So the answer for that is because the strength of the IMF, of their IMF, determine their state of matter, and we're going to take a look at why each of these have different strength of IMF. Okay, so let's take a look at the first question that we're going to take a look at next is that, well, because IMF strength determines state of matter, and we have different type of IMF, then the next question is, what determines the type of IMF then? Okay, so the answer is molecular polarity. Okay, so molecular polarity would determine the type of IMF, and the type IMF will also determine this. You can tell the strength by that as well. Okay, so how can we determine the molecular polarity then? So this is going to go back into Chem 121 again. Okay, so in Chem 121, you learn about molecular geometry and also the overall dipole moment. Okay, molecular geometry and also the overall dipole moment would determine the molecular polarity. Okay, so let's review Chem 121. Okay, so these additional slides, I'm going to post it on Moodle. You are welcome to print it out, or you can just have it open in a different tab. That's fine as well as you watch this video. Okay, so let's take a look first at bond types. Okay, so bond types that we learn in Chem 121, there are 3 different kinds, right? So you learn about ionic bonds, right? You learn about polar covalent bond and also non-polar covalent bond. Okay, so in order to tell whether they are polar covalent or pure covalent or ionic bond, you can do 2 things, right? A general idea would be if you have metal, non-metal, right? So that's going to be ionic bond, right? If you have metal plus non-metal, if you have all non-metal together, it's going to form covalent bond. So that's kind of like a general idea of it. But the real actual things that determine whether it's polar or non-polar is come from the difference in electronegativity value. Okay, so this En is the electronegativity value. So electronegativity value from what you learn in Chem 121 tell you about ability of the atoms to withdraw electron toward itself, right? If the atom want to withdraw electron toward itself a lot, it's going to pull that toward itself. And if the other one doesn't want to withdraw any electron, it's going to give off that electron to the other atom. So that's what causing the charge separation, right? So in this case, if you see the difference in En between 0 to 4, we can say that that is going to electron within that molecule is going to share equally. So we call this bond non-polar, right? So if you have the value between like 0.5 to 2, right? So that is going to fall into polar bond, right? And if you have anything greater than 2, that is going to fall into the ionic bond, because one is going to pull electron away from the other, right? So so the greater the En, right, the bond become more and more polar. Okay, so that's what we see from here. Okay, so that's pretty much what we see in Chem 121. You learn how to calculate for that, right? So by using this value to calculate for all of these value, right? So these value are the difference between the 2 atoms within the bond, right? So, and these are the list of the value. And these difference in En value would tell us about bond polarity, but bond polarity is not a final answer to the polarity of the molecule. Okay, so it's just part of it. Okay, so it's one of the puzzle. So the next thing we need to take a look at is we need to take a look at the molecular geometry or the shape of the molecule. Okay, so we're gonna take a look at the 2 theories that we learned in Chem 121. One is the VSEPR. So there is the typo here. So can you actually change that to PR? Okay, so it's the valence shell electron pair repulsion. Okay, so and another one is valence bond theory. Okay, so these 2 theory tell us about the shape of the molecule. Okay, so valence bond theory tell us about the hybridization or how the bond is being formed. Okay, so these are the electron domain, which is the electron group around the center, like the center atom or the central atom. Okay, so and according to the number of electron group, you can also determine the electron domain geometry as well. Okay, or the shape of the what do you call it, electron around the central atom, and the number of lone pair would dictate the molecular geometry. Okay, so if you have lone pair, right, so you are going to end up with different molecular geometry from the electron domain geometry. Okay, so all of these you are going to have to recall from Chem 121 again. Okay, so the molecular geometry and along with the overall dipole moment going to help us determine molecular polarity. Okay, so let's take a look at what if you have a linear geometry. Okay, so if you have linear geometry, and let's say if you have central atom here, and this is the outer atom, right? So this is the outer atom. If the outer atom are the same, or if these 2 bonds are non-polar bond, you are going to end up with the non-polar molecule because they are pull each other equally in both directions. Therefore, the overall dipole moment will equal to 0. So there is no dipole at all. There is no separation of, like dipole between those 2. However, if you introduce one side to have a greater polarity than the other, that's when you are going to end up with the polar molecule. Okay, so that means whenever that you introduce asymmetrical to the molecule, you are going to end up with polar molecule if the bond is polar. Okay, so in this case, if you have in this case, if you have non-polar bond, right, and then non-polar bond, you are going to end up with non-polar molecule. If you have polar bond and polar bond and they are pulled equally, you are going to also end up with the non-polar molecule as well. Okay, so this is I'm talking about bond. This is I'm talking about molecule. Okay, so this is the overall molecule. Okay. However, again, if you have one pull toward itself stronger than the other, you are creating a symmetrical what do you call like dipole. In this case, you are going to end up with a dipole moment, and the molecule would be polar. Same thing, you're looking at trigonal planar. In this case, this is the shape of trigonal planar, where you have the central atom, right? And then you are going to have three, what do you call, surrounding, right? So, or three electron group. This electron group, again, can be atoms, three different atoms, or it can be lone pair, right? So from what we learned in Chem 121, so it can be either of those. But if you are having them pull in all those directions equally, you are going to end up with non-polar molecule. Okay, so however, if you introduce any of these if you introduce any asymmetric into the molecule would be polar, right? So in this case, it's pull toward this direction stronger than the other two. Okay, so same thing as well. If you have like this one pull really strong, this one pull really strong, this is going to be polar molecule as well. Okay, so tetrahedral, you are going to see like a what do you call like a pyramid with one going up. So this one, if you have everything the same, you are going to end up with non-polar molecule. And then if you introduce any of those asymmetric, you are going to end up with polar molecule. Okay, so same thing with trigonal bipyramidal as well, right? So those are going to be non-polar if it's pulled equally in all direction, and it's going to be polar if one is going to go toward one direction over the other. Okay, so same thing for octahedral as well. Okay, so if you introduce any of these, it would be polar. Okay, so one thing I want to point out is that if you have octahedral, right, and if it's like, let's say like if you pull these together with the same force, this one would then end up with non-polar. Okay, so it's depend on how many you are going to introduce within those electron group. Once you are able to determine the polarity of the molecules, this polarity of the molecule, whether they are polar or non-polar, would help us determine the type of IMF. Okay, so let's take a look at the first type. Okay, so the first type of IMF is called dispersion force or London force. Okay, so dispersion force is the weakest IMF that account for the attraction between all molecules, regardless of whether the molecule is polar or non-polar. Dispersion force appear in all molecules. Okay, so I'm going to start with the nonpolar molecule because it's just easier in this case. So the nonpolar molecules such as hydrogen molecule, right? So we have two hydrogen molecule here. Okay, the force that responsible for this interaction, this two molecule interaction, is called dispersion. Okay, so dispersion is going to come from the unequal distribution of electron within the molecule. Okay, so what do we mean by that? Let's take a look in just a few minutes here. This type of force is going to be just temporary. Okay, so this is temporary dipole. Okay, so this attraction force is temporary. Okay, so I want you to highlight that. Okay, the reason why it's temporary because if you're looking at the bond within this, right? So this bond right here is non-polar, which means that the electron within this molecule should should have equal distribution, right? Because they are going to pull electron equally. So how can that we do observe unequal distribution of electron? This unequal distribution of electron in the nonpolar molecules occur when you're looking at the instantaneous moment. Okay, so if you're looking at the atomic particle view, like such as atom A like this, okay, so if you're looking at the polarization, you are going to see that the electron are going to distribute equally throughout an atom. This is the picture that we see here is static, right? It's not moving. We see that the two electron would be try to like stay as far as possible because they have negative charge, so they repel each other, right? So they want to stay away from each other. So this is just static. However, in reality, when you have an atom, right, or even molecule, the electron within atom or molecule is going to move around, and eventually at an instantaneous moment, you are going to see as well those electrons sometimes gonna go to one side to over the other, right? They're not gonna try, what do you call it, they're not gonna always gonna stay away from each other, right? Because they move all the time, so in this case, you can see as well that atom B, for example, those two electrons are eventually gonna move and somehow they're gonna move closer together, right? So again, it's dynamic, right? So this is dynamic picture at instantaneous moment. And this moment right here that happened not very long, that's why it's considered to be a temporary dipole, right? This instantaneous moment that is happen is going to generate the polarized charge, right? So that means in this case, the size of the atom A that contain more of the electron would be partial, right? So this is partial charge, partial negative, and the other one that is lacking electron would be partial positive. This is what we call instantaneous dipole, because you are having a dipole moment that occur within an atom or within the nonpolar molecule in this case. Okay, this instantaneous dipole that happen at instantaneous moment is going to induce another atom as well. Okay, so because this electron right here is negative, right, is want to attract a nucleus of the other atom, so therefore it's going to push the other two electron to be away from this side, right? Because remember, electron repel, right? Therefore it's going to push this electron to be on the other side. So in this case, it's going to cause another molecule to also have a dipole moment as well, or is creating a partial positive and partial negative that they can attract to each other, right? So this is why it's called induced dipole, because atom B induce the dipole moment to happen in an atom A. So again, this is happen only an instantaneous moment. So therefore, in this case, we can say that this force, this attraction force right here that happen is going to occur temporarily. This dispersion force right here is going to be the weakest type of IMF, because it's not permanent, it happened and at the instantaneous moment. The next thing we are going to take a look at is the factor that affect the strength of dispersion force. And the first factor we are going to take a look at is the molar mass. Okay, so go back into the example that I mentioned earlier, right? So we looking at a different state of chlorine, bromine, iodide, that they are located on the same group in the periodic table, right? So if you're looking at this, you will see that chlorine, bromine, iodide have different molar mass. In this case, chlorine is the lightest and iodide is the heaviest. As molar mass increase, the number of electrons increase as well. As the number of electrons increase, the instantaneous dipole and the induced dipole will occur easily, causing the strength of the dispersion force to become stronger, resulting in the denser state in this case, because molecule would be close together. They want to like pull each other closer together, right? So therefore, it's going to go toward a denser state. Same effect you can observe with hydrocarbon compound as well. For example, propane, octane, and wax, right? So again, hydrocarbon refer to the compound that contain carbon and hydrogen. Okay, so as you see here, as the molecule become bigger and bigger, right? So you're going to see that as molar mass increase, but dispersion force also increase as well, and it's going to result in denser state as well. Okay, so going from gas to liquid and to solid here as the number of carbon increase. Intermolecular forces also have an effect on melting point and boiling point as well. Melting point is going to be the temperature at which solid become liquid, and boiling point is going to be the temperature at which liquid become gas. Okay, so if you're looking at this, right, so as we see in the previous slides, we see that the temperature is going to be related to kinetic energy, and that is going to also related to the strength of the IMF as well, right? So in this case, if you're looking at this, if you think about it, right, so if you want to change from solid to liquid, the state of matter need to what do you call, like the IMF that hold within the solid need to be loose, right? So they cannot, so that way they cannot, what do you call, like hold together too like strongly. So in order to do that, you need to input the energy, right? If solid itself doesn't have a strong IMF, then the energy input would be less, right? So you are going to end up observing a lower boiling point. Vice versa, if the IMF within the solid is really strong, the solid doesn't want to separate from each other, it's going to require more energy to separate them. Therefore, you are going to observe the higher temperature for melting point. That same thing for boiling point as well. So in this case, if you're looking at molar mass of these molecule, right? So these molecules are non-polar molecules, so they exhibit only dispersion force. And again, as I mentioned earlier, the strength of the dispersion force is directly proportional to the molar mass. So therefore, as the molar mass increase, right, you are going to observe a stronger IMF in this case. And as the molecule exhibit a stronger dispersion, you are going to observe as well that their melting point and boiling point is going to be high. Now, if you're looking at this table and compare between astatine and fluorine, right, you will see that because astatine has higher molar mass than fluoride, therefore astatine going to have a stronger dispersion force. The force that hold between the molecule of astatine together would be stronger than fluorine. Therefore, in order to separate those molecules to change from solid to liquid or from liquid to gas, is going to require much more energy than of the fluorine, right? So that's why you will see that those have higher boiling point than the fluorine. Next, we are going to take a look at another factor that have on the strength of the dispersion force, which is molecular shape. Okay, so I'm going to use the pentane scenario in this case. So we have 3 different types of pentane. Okay, so they have the same number of carbon and hydrogen. Okay, so all of these have the same number of carbon and hydrogen. The only thing that different for all of these 3 are the shape of the molecule. Okay, so this one is look kind of like a sphere, right? This one is look like a branch. Okay, so this one look like linear. Okay, so those are I'm going to refer as branch and linear. Okay, so if you're looking at molar mass, because they have the same chemical formula, they are going to also have the same molar mass as well. So therefore, in this case, because all of these molecules have the same molar mass, therefore the molar mass will not have an effect on dispersion force in this case, right? Because they all have the same thing. So I cannot use molar mass to actually determine the strength of dispersion. But you can tell that they have different strength of dispersion force. The reason for that is because they have different value of boiling point. As I mentioned earlier, right, the higher boiling point indicate that there are the force between the molecule are stronger, right? It's require higher energy to change the state from liquid to gas, right? So in this case, we can see that the pentane has the strongest IMF, right? So in this case, it's going to be the strongest dispersion in compare to neopentane. Okay, so why is that? Okay, so the next thing we're going to take a look at is we're going to looking at the surface area or the surface of interaction. If you're looking at the surface of interaction, this chain structure right here has a larger surface interaction, right? In comparison to like this neopentane that have kind of like a ball, right? So the surface interaction is going to be just that. So in this case, the larger area for the interaction would allow them to attract each other stronger. Therefore, in this case, going to end up with the stronger dispersion force. And as you can see, right, the boiling point increase. Okay, so that means if you're looking at the type of dispersion, whatever that have higher molar mass is going to have higher boiling point and higher boiling point as well because have stronger dispersion force, right? However, if you compare the same molar mass, okay, the same molar mass, the next thing you're going to look at is the shape of the molecule, right? The molecule that have shape that allow for a larger area for interaction is going to also have the stronger dispersion, and it's going to end up with a higher boiling point and also higher melting point as well. Okay, so that's the conclusion of this. So with that being said, so the next thing I would like you to do is to looking at example 1 with me. Okay, so in this case, we have propane and then 2 different type of butane. Okay, so what I'm gonna do is that I'm gonna use the idea of the strength of the dispersion force and to help us determine the relative boiling point. If you're looking at propane and butanes here, you will see that the type of bonds, which is carbon and hydrogen, right? And carbon-carbon, those type of bond are non-polar, is making all of this molecule to be non-polar molecule. Therefore, whenever that you see carbon-hydrogen or carbon-carbon, note that those are going to be non-polar bonds. And if you have molecule that contain a lot of non-polar bonds, the molecule would be non-polar molecules. So in this case, all of these are non-polar molecules. Therefore, the type of IMF that present in this molecule would be dispersion. And as I mentioned earlier, the factor that determines the strength of dispersion force would be molar mass, right? And if the molar mass are equal, then you're looking at the shape of the molecule. So in this case, if you're looking at molar mass, propane has the least amount of carbon, it's going to have the lowest molar mass, right? And between butane and the N-butane and I-butane, you will see that they both have the same number of carbons and also same number of hydrogen as well. Therefore, they both would have the same molar mass. So in this case, what I know for sure is that I know that the lowest molar mass, which is propane, would have the weakest IMF, right? So the weakest strength of the dispersion, okay? And therefore, it's going to have the lowest boiling point as well, okay? Now, if you're looking at N-butane and I-butane, you see that they both have the same molar mass. Therefore, I cannot use molar mass to compare the strength of dispersion between those two. The next thing I'm going to look at is going to be the shape of the molecule. Okay, this molecule here is in a linear, right? This molecule is kind of like in a ball, like a branch structure. So therefore, the linear would allow for a larger area of interaction in comparison to a branch structure. Therefore, in this case, larger interaction would lead to a stronger dispersion. So in this case, the N-butane would have the strongest IMF, and therefore the N-butane would have the highest boiling point. The next IMF that we are going to take a look at is dipole-dipole attraction. Okay, so dipole-dipole attraction imply, right, these are going to happen between the molecule that contain dipole moment, which are the polar molecules. Okay, so the attraction between polar molecules are going to be due to the permanent dipoles. Okay, so because permanent by dipole is not a temporary, like the previous case that we see, therefore in this case, the dipole-dipole attraction would have a stronger attraction than the dispersion force that we see previously. For example, if you have two polar molecules here, right? So one polar molecule's its partial negative charge is going to attract to the other polar molecules partial positive charge, right? So in this case, you will see that the two adjacent polar molecules will attract to each other. Okay, so attraction between these two are going to again be coming from the opposite partial charges. Okay, so note that it's going to come from the opposite partial charges. So in this case, if you're looking at HCl, for example, right? So HCl is polar molecule. In this case, you are going to see that the chlorine partial negative charge from chlorine is going to interact with the partial positive charge of the hydrogen of the adjacent molecules. Okay, so again, note that this attraction is permanent. Okay, so it's not temporary. This is permanent. Therefore, the dipole-dipole would be stronger than the dispersion, always going to be stronger than dispersion. All right, so I have an example here. Okay, so I'm going to use the strength of the IMF again to determine the relative boiling point. And as I mentioned earlier, right, so the boiling point is going to be directly proportional to the strength of the IMF. Okay, so in this case, we are going to predict which one would have higher boiling point. Okay, so we have nitrogen gas and carbon monoxide. Okay, so I'm going to review Lewis structure a little bit from 121. Okay, so if you want to draw nitrogen gas, okay, so first you count number of valence electron first, right? So you have 2 nitrogen and each nitrogen have 5 valence electrons, so total would come equal to 10. And the next thing is you are going to put a skeleton, right? So nitrogen, you are going to start with a skeleton, right? So you can start with single bond first and then go with double bond and then go with triple bond, right? So this 4 bond right here is not going to be valid. Okay, so I'm going to cross that. So I'm going to use just triple bond. If you have triple bond, you already use 6 electron total. So you are having 4 electron left, and that 4 electron left is going to go as the lone pair for those two. Okay, so if you're looking at this, you see that those two atoms are going to, is the same, right? So therefore, in this case, the bond polarity between those two would be non-polar bond. So therefore, this molecule would be non-polar molecule. Okay. Now, if you do the same thing with carbon monoxide, right? So carbon 4, oxygen 6, valence electron add together is equal to 10. So if you do the same thing, right, you start with skeleton and distribute off those, what do you call, like remaining electron as lone pair. This one is going to be lack of octet. Therefore, I'm going to make a double bond, right? So double bond also lack of octet as well, right, on the carbon. So therefore, you're gonna do triple bond. So if you do triple bond now, both carbon and oxygen meet octet now. So this is a good Lewis structure. Okay, so once you know that, then you know that oxygen has higher En value than carbon. So oxygen going to pull electron toward itself away from carbon. Therefore, in this case, this molecule going to be polar molecule. Okay, so we know one is non-polar, the other is polar. Therefore, the type of IMF that present in these two would be, for nitrogen, would be dispersion, carbon monoxide also dispersion as well. Remember, all molecules exhibit dispersion. Therefore, in this case, all molecules gonna have dispersion. But because carbon monoxide is a polar molecule, therefore it's going to exhibit dipole-dipole as well, right? Because dipole-dipole is going to be present in the polar molecule. So in this case, because dipole-dipole is the what do you call permanent dipole interaction, therefore in this case, it's going to have a stronger strength of IMF than the dispersion. Therefore, in this case, carbon monoxide would have higher boiling point because it has stronger IMF in this case. Okay, so what you are going to do is, if I would summarize from what we see previously, would be you are going to have to determine first which one would be the correct type of IMF. The stronger type would have a stronger strength, right? So for example, in this case, dipole-dipole would have a stronger strength than dispersion. And if you end up with the same type of IMF, the next thing you're gonna look at is the molar mass. If the molecules have the same molar mass, then the next thing you're gonna look at is the structure, right? The surface area for interaction. Okay, so that's kind of like tied back into the previous slide that we just went over. Okay. All right, so the next thing we're gonna take a look at is example 2. So in this case, we are going to sketch a graph. Okay, so we're gonna plot it against between boiling point against molar mass. Okay, so I have 4 molecules. I would like you to cross out the last one. Okay, so we are going to cross out the last one. Okay, so we'll cross out this one. Okay, so what I'm going to do is I'm going to start with methane first. Okay, so in this case, if you're looking at the structure, okay, so because this is for electron domain, but if you add carbon in the middle, okay, so all of this would be hydrogen. So this is tetrahedral. And because the molecule of this bond are non-polar bond, and if you're looking at, right, so this polar bond, the En carbon is actually having a little bit slightly higher En value than hydrogen, so it's gonna pull toward carbon, but it doesn't matter because this molecule is gonna be non-polar anyways, because the bond between carbon and hydrogen of these are non-polar bond. Therefore, this molecule would be non-polar molecule. Because this molecule is non-polar molecule, therefore this molecule would exhibit dispersion only. Okay, you can do the same thing for CH3B as well. So you introduce bromine. In this case, you introducing bromine. Bromine has higher En value than carbon in this case, right? So therefore, the direction of the dipole moment will go toward bromine. Therefore, in this case, this molecule is going to be a polar molecule. Because CH3B, right, is polar molecule, therefore, it's going to exhibit dispersion and also dipole-dipole as well. Okay, same thing, you have CH2Br2, right? So carbon would be in the middle and you have 2 bromine, okay, that pull electron away from carbon. So therefore, this molecule also going to be polar molecule also. And this molecule is going to exhibit dispersion and also dipole-dipole. Okay, the last one, if you do the same analysis, okay, so you are going to end up with 3 bromine, right, and then carbon, and then this hydrogen. So everything pull toward bromine. So therefore, there's nothing to cancel that. So in this case, the molecule is still gonna be polar molecule, and the type of IMF would be dispersion and dipole-dipole still. Okay, so the next thing we're gonna take a look at is, well, we know for sure that the dispersion is the what do you call it, is the weakest, right? This is the strongest. So in this case, what we know is that we know this is gonna have the lowest boiling point, right? Because it's have only one type of IMF, and it's the weakest IMF as well. Now with these three, okay, so you end up with the same dipole. All of these are the same. So the next thing we're gonna take a look at is we're gonna take a look at their molar mass. Right, so the heaviest molar mass would have the highest boiling point. Right, so that's how I compare. Okay, so I look at the type first, and then if they are the same type, then you're looking at molar mass. Okay, so now with that being said, what we see is going to be the methane would have the lowest boiling point, right? And then CHBr3 would have the highest boiling point. The reason for that is because this one has the highest molar mass. Okay, because all these three, they are going to what do you call? They are going to have the same type of dipole, but this one have the highest molar mass, so this one gonna have highest boiling point. Okay, so now you plot graph. Okay, so we want y-axis to be boiling point, okay, and we want x-axis to be molar mass. Therefore, in this case, you are going to plot CH4 right here. And because this portion is going to be the weaker than dipole, therefore CH3b would be up here, right? And then CH2br2 would be up here, and then the highest one would be CHBr3. Okay, so that would be the relative boiling point for this. Okay, so again, it doesn't have to be exact. Okay, so it's relative. So as long as you get the relative value, that should be good. Okay, so on the exam, I might ask you to plot graphs the same. So the same analysis, right? So you go by the type of IMF first. If they're the same type, then you're looking at molar mass. If they have the same molar mass, then you're looking at the shape of the molecule. All right, next one. Okay, the next type, the last type of IMF that you are going to learn from this lecture is going to be the hydrogen bonding force. Okay, so the hydrogen bonding force is the special type of dipole, but it's got a new name because this is the strongest one. Okay, so it's even stronger than the dipole. Okay, so this strong IMF force that is going to occur between the hydrogen atom that bond directly to fluorine, oxygen, and nitrogen. So again, the keyword is hydrogen bond directly with fluorine, oxygen, and nitrogen. Okay, what is the hydrogen bonding exactly? Okay, so I'm going to give an example of ammonia. Okay, so for example, in this case, if you have ammonia, you will see that hydrogen bond directly to nitrogen. Okay, so if this ammonia is come close to water, okay, so molecule of water, the lone pair of the oxygen, which is adjacent to the ammonia, this partial negative charge is going to interact with this partial positive charge of hydrogen that bond directly to nitrogen. Okay, so this bond right here is what we call hydrogen bonding. Okay, so again, hydrogen bonding comes from the hydrogen that is going to interact or attract to the lone pair of the nearby oxygen, fluorine, or nitrogen. But this hydrogen right here has to bond directly to nitrogen, oxygen, or fluorine. Okay, so we call the hydrogen, the partial positive hydrogen that is being part of the hydrogen bonding, we call hydrogen bonding donor. And the oxygen lone pair is what we call hydrogen bonding acceptor. Okay, so this accepts the hydrogen partial positive charge. Okay, so if you're looking at this water molecule here, so of course water, the special property of water is actually caused by hydrogen bonding force. Okay, so if you're looking at this water, you will see that all of those hydrogen would be hydrogen bonding donor, and all those oxygen would be hydrogen bonding acceptor. Okay, so now let's take a look at example here. Okay, so this is the amino acid. Okay, so I would like you to go ahead. When you see the hydrogen bonding donor, I want you to circle it, and I would like you to square the hydrogen bonding acceptor. Okay, so in this case, hydrogen bonding donor would be those hydrogen that are directly attached to oxygen, right, or nitrogen or fluorine. So that means these three are the hydrogen bonding donor. These two are not, okay, because not bond directly to nitrogen or oxygen or fluorine. Okay, now the hydrogen bonding acceptor are the lone pair of oxygen, nitrogen, or fluorine. Okay, so the nearby. So in this case, all of these would behave as hydrogen bonding acceptor. You might ask, wait a second, but this one right here doesn't have hydrogen though. That's fine, as long as if the acceptor are the lone pair of oxygen, nitrogen, or fluorine, those can be acceptor. Okay, so as long as they have lone pair. All right, the next example is I would like you to pause this video and find the hydrogen bonding donors and hydrogen bonding acceptors and resume the video again when you finish. Let's check your work together. Okay, so hydrogen bonding donors are those that attach to hydrogen, oxygen, or fluorine directly, right? So in this case would be these three. And hydrogen bonding acceptors can be any of these that have lone pairs. Okay, so the two examples that I show you, one is amino acid, right? This is the base found in DNA and RNA. So if you're looking at this, the hydrogen bonding forces is actually very important because it's actually responsible for the secondary structure and tertiary structure and quaternary structure in protein, and also the helix structure of the DNA and RNA as well, right? Because of all of these hydrogen bonding. The hydrogen bonding forces are also responsible for the strength property of water as well. Okay, so just recall from chapter 8.2 that we learned earlier. So whenever that you see different temperature, right, you will see that most substance would expand as the temperature increase, and most substance will contract as the temperature decreases. And that is going to cause the density of matter change as well. For example, as the temperature increase, right, the substance expand, and that is going to increase the volume. Therefore, the substance will become less dense. Versus if you have the substance at lower temperature, right? So it's going to contract, and that is going to cause the volume to shrink, right? So therefore, in this case, the substance would become denser, right? So that's what we looking at in chapter 8.2. This fact also true for water as well, but it's only to a certain degree Celsius. Okay, so for example, the picture that you see here is in the summer. Okay, so at the lake, you will see that at the surface of water that is exposed to the sun is going to get warmer. So therefore, as the temperature increase, it's going to, the density is going to decrease, right? So therefore, in this case, water at 25 degrees Celsius would have lower density than at 4 degrees Celsius. So in this case, you will see that water at a higher temperature would rise to be the top of the surface, right? And water that have a a denser state would be at the bottom. Okay. And when the fall times come, right? So the temperature drop. This temperature right here is going to get closer and closer together. Therefore, it's going to become more uniform. Therefore, you are going to observe the circulation of water, right? So the water mixed within the lake. And then when the winter hit, you are going to observe that the surface of water become colder and colder up until it's colder than 4 degrees Celsius. Okay, so once it's reached 0 degrees Celsius, okay, so the water is actually less dense. Okay, so as you see that water at 0 degrees Celsius is actually less dense than at 4 degrees Celsius, which is contradict to what we see earlier, right? So the earlier we see that as the temperature go down, as the temperature decrease, the density should also increase as well. But in this case, the opposite. Okay, so that's what we're going to take a look at. We're going to take a look at how come that water as is get colder than 4 degrees Celsius, how come that it's become less dense? That's what we're going to take a look at. The fact that water become less dense as it get colder than 4 degrees Celsius is actually very good for ecosystems because it's allowed the organism in the lake to survive during the cold winter. And when the springtime comes, right, when it gets warmer, the temperature of water become a little bit more uniform. It's going to causing the water circulation again, and then it's reaching to like the summer scenario again. The reason why water become less dense at the temperature below 4 degrees Celsius is because water molecules start to form hydrogen bonds in hexagonal structure, and this hexagonal structure causing the volume of water to expand. So therefore, in this case, you will see that the ice would expand, right? Because the volume of ice get bigger. And therefore, in this case, as the volume expand, the density decreased. Okay, so therefore, in this case, ice would float in water. All right, so hydrogen bonding also responsible for other property of water as well, such as high surface tension that we're gonna learn in later on in this chapter, and also causing water to have high heat of vaporization as well. Okay, so all of this due to hydrogen bonding. All right, example 2, if you're looking at the graph plot between boiling point against molar mass, you will see that water has the highest boiling point, right, in comparison to all of this that has higher molar mass. Okay, so the reason for that is because the type of IMF that present in water, right, which is the hydrogen bonding, is the strongest, right? It's stronger than any of these that you see, even though they have higher molar mass. But in this case, because the IMF in water is actually hydrogen bonding, which is the strongest IMF, therefore water would have higher boiling point in this case. All right, so the next thing I would like you to look at is, I would like you to think about this, for example, here. I would like you to plot the graph between boiling point versus molar mass. Okay, so the y-axis would be boiling point, okay, and then the x-axis would be molar mass. Okay, so I would like you to pause the video now and then think about the type of IMF, and then you can plot the graph. Okay, so and then check your work against my work after you're done. All right, let's check your work together. Okay, so if you're looking at the location on the periodic table, you will see that fluorine would be lighter than iodine. Okay, so in this case, fluorine would be around here, right? This is low, right? This is low molar mass to high molar mass. Okay, so that means HF would be around here, right? And then followed by HCl, followed by HBr, and then followed by HI. But the location on what do you call, like the difference would be the location, the relative location of the boiling point. Okay, so if you're looking at the type of IMF, okay, so all of these molecules are polar molecule, therefore they would have, so all of this has dispersion. Okay, all of this has dipole because they all are polar molecules. The only special things that no other molecule has would be hydrogen bonding. Okay, so hydrogen bonding occur only with HF. Remember, hydrogen bonding is occur when hydrogen bond directly to fluorine, oxygen, or nitrogen. Right? So in this case, HF would be would contain hydrogen bonding. The question is, which type of IMF is the strongest? The answer is hydrogen bonding. Right? So in this case, HF would have the highest boiling point. Okay, so it should have the highest boiling point because it contains the strongest type of IMF. Now, because of these three, okay, so HCl, HBr, and HI has the same type of IMF, the next thing you're going to look at is molar mass, right? The higher molar mass would have the stronger IMF, therefore the boiling point would be higher. So therefore, if I plot this graph, the correct graph of this would look like this. HF would be right here, right? Because have the strongest IMF, followed by HCl, followed by HBr, and followed by HI. Note that HF would still have higher molar boiling point than HI in this case. Here's a summary of the IMF that we learned. Okay, so the strength going from the weakest to the strongest, right? So hydrogen bonding is stronger than the dispersion and dipole. Here are more examples that you can work on. Okay, so practice this and then check your answer against the key that I will post on Moodle. Here's a summary for this chapter that will help you to do your homework and start working on your homework as soon as possible.